In this last video, I'd like to talk about some properties of the definite integral. First of all, if we were to integrate from a to b, the function f of x, and I want to consider how that relates to the integral from b to a, it turns out that we just have to have a constant multiple of -1 out front. To think about why that would be true, in terms of our definition, if we were to compute delta x for the integral on the left, we would take b minus a over n. But notice that that's the same thing as -1 times a minus b over n, which would be -1 times the delta x for the integral on the right. If you were to integrate from x equals a to x equals a, so you have the same lower and upper limit of integration, this should give us 0. And again, a quick check as to why. Computing the delta x here would involve the length of the interval being 0, and so it's really the rectangle width being 0. Next, think about integrating a constant function. We've seen this for the constant 2 in recent videos. This is always going to yield us here c, the constant, times the length of the interval. And this is for c, any constant. Another property dealing with constants is a constant multiple. If I integrate from a to b, c times f of x, that's equivalent to c times the integral from a to b of f of x. This actually stems from one of our properties of sigma notation that we saw in an earlier video. We saw another property of sigma notation dealing with sums, and that's going to result in the next property. If I were to integrate from a to b, f of x plus g of x, that's going to be equivalent to taking the integral over that interval of f of x and adding it to the integral of g of x. We can combine properties 4 and 5 with our constant c being a -1 there, and that would give us a similar property looking at the integral of differences. Next, if we think about integrating from a to c, our function f of x, and then we add to that the integral from c to b of the very same function, that is going to be equal to just integrating from a to b. And it turns out this holds for any relationship between a, b, and c with regards to where they lie on the number line. And then finally, the last property I want to look at, if we know that f of x is always less than or equal to g of x on our interval of interest, this is going to lead to the integral of f, the smaller function on that interval, being less than or equal to the integral of the function g. Okay, now that we have those properties, let's put those into use. So in this next example, we have an arbitrary function f of x, and all we know are the following things: that the integral from 0 to 5 of this function is 4, and the integral from 0 to 8 of this function is 16. With just that information, let's find the following. So first of all, if we were asked to find the integral from 0 to 5 of 3f of x, we have from our property above with multiplicative constants that should equal 3 times the integral from 0 to 5 of f of x. From the given information, that's 3 times 4, so this would have to equal 12. If we're asked to find the integral from 5 to 8 of f of x, we can think about how we would do that using our property let's see, number 6, where we could kind of rearrange that, notice that this should be equal to the integral from 0 to 8 of f of x minus the integral from 0 to 5 of f of x. And filling in those given values, that's 16 minus 4. So we would likewise get 12 here. And finally, if I was asked to find the integral from 0 to 8 of 5 plus f of x, this is going to, yet again, use several of the properties above. First of all, I can split that into the integral from 0 to 8 of 5 plus the integral from 0 to 8 of f of x. Now, we're given the second integral there, and the first one is the integral of a constant, which we have a property for that. That should be 5 times the length of my interval plus the given integral being equal to 16. So 40 plus 16, and we get 56. So another example. Suppose we have a piecewise function. We can actually use our properties before to evaluate integrals of piecewise functions. So we want to find the integral from 0 to 5 of f of x, where the function f of x is piecewise defined as equal to 10 when x is less than or equal to 3, and equal to minus 2 when x is greater than 3. So in this instance, I want to find the integral over the interval from 0 to 5, and in some sense there's this change in the function at 3. So we can use our property, I think it was property 6, yet again, to break this up as the integral of this function from 0 to 3 plus the integral from 3 to 5. And once I've broken it up in that way, when we're looking at the interval 0 to 3, f of x is defined to be 10 there. But as soon as I get from 3 to 5, f of x is defined to be minus 2. Again, I have the integral of constants, so I have 10 times the length of my interval plus negative 2 times the length of my interval. I get 30 minus 4, or 26. And then finally, we haven't really seen the use of our last property that I wrote there. And that's, now I can come back to that and thinking about coming up with bounds. Suppose the only thing I know about my function is that 3 is less than or equal to f of x is less than or equal to 8. Then my question here is between what two values can we bound the integral from 0 to 2 of f of x? So kind of considering what the bounds on the function f, how that gives us bounds on the integral. So I'll point out, of course, we don't know what f of x looks like, but what I do know, let's see, we're looking at 0 to 2. Suppose these are my axes. If this is 8, and let's say this is 3, I know that my function effectively can't dip below the dotted line at 3 or above the dotted line at 8. So you could imagine that maybe my function looks something like this on my interval. And of course, we are just concerned with the interval from 0 to 2. And we are trying to come up with bounds on this area. And of course, I don't know that this is the graph of f, I'm just drawing a representation. So what I want to bring in is the bounds on f. So for a minimum, let's use blue, notice that I am guaranteed that if I take, whoops, let's use the pen here. I am guaranteed that if I take the rectangle with height equal to 3, the minimum possible value of f of x, even though this is just a representation of the graph, I'm guaranteed that this rectangle has to sit inside of the shaded area. So that tells me that in terms of coming up with a lower bound, so we have 0 to 2 of f of x, I know now from my blue rectangle that the rectangle with width 2 and height 3 must sit inside of that area, so we must have a lower bound of 6. With regards to the upper bound, in a similar way, I'm guaranteed that if I consider the rectangle which has height equal to 8, the maximum value of my function f, that has to be a rectangle that entirely contains the area that we're interested in, the yellow area there. So that means I get an upper bound if I take the rectangle area, which we have height 8 times, again, the width 2, so we get our upper bound of 16. I'll also point out, to bring this back to something we've seen before, effectively, notice that I'm using the max and the min Riemann sum where we have n equals 1 rectangle here.